Okay, for chapter 4.3, we're going to be talking about how derivatives affect the shape of the graph. So I have a little graph drawn here just so we can kind of talk about it. And in red, I have if if f prime of x is greater than 0 on AB, then f of x is increasing on AB. And if f prime of x is less than 0 on AB, then f of x is decreasing on AB. Okay, so basically, this is our f of x, right? And what this is saying is that based on the derivative, you can talk about what the actual function is doing. So again, we can think about it like this. If f prime of x is greater than 0, so remember the derivative means slope of the tangent line, okay, or the instantaneous rate of change. So if we were to just look right here, our derivative, the slope of our tangent line would be positive. It would be an increasing slope. So that's what this is talking about right here. This is talking about that if f prime of x is greater than 0, meaning if f prime of x is positive, then on this interval that you're talking about, f of x is increasing. And again, they say positive anywhere on this interval. So no matter where I pick, right, if I pick instead of right there, if I pick instead of right there, let's say I try here and I draw my tangent. Still, it's positive. What if I pick right here? Still positive. So no matter where I pick on my graph, I still get a positive slope. So this symbolizes that the graph must be increasing at this point, at this interval. Okay. Now they do the same thing over here, and we discuss if f prime of x is less than 0, meaning negative. So then we come over here and we try to draw a little bit. So let's go on this interval. So let's say we're here. If I draw a tangent line here, I would be negative. If I draw a tangent line here, I would be negative. So it really doesn't matter where I draw my tangent line, correct? In this interval from B to C. And the problem, this is the general intervals A to B. So I'm just saying if I wanted to find a decreasing one, I would have to go to BC, okay? So in general, if you have some interval and the derivative is always positive on that interval, then you can say that it is increasing. So on that interval, or if it's always negative, the derivative is always negative, then you can say it's decreasing. And all you have to do graphically is look at the slopes. So basically what we're going to discover in this section is how derivatives can affect or define, or I guess not define, describe to us characteristics of a graph, okay? So we come over here and we say, if f prime of x changes from plus to minus, so from positive to negative at a critical number c, then there exists a local maximum at x equals c, okay? So that makes sense. Now think about it. If we're going from a derivative being positive, so kind of pretend, you know, we're here, and then we're here, and then we're here. All these derivatives are positive. All these slopes of these tangent lines are positive. And then all of these derivatives here are negative, right? So we got all these tangent slopes right here that are negative. So somewhere in there, they're saying there had to be a critical number. And remember, a critical number is when the derivative is equal to 0 or it's undefined. Well, if you go from increasing slopes to decreasing slopes, somewhere in there, you had to get a horizontal tangent. You had to get a slope equal to 0. And they're saying when you go from plus to minus, you are going to get a local maximum, which this is. This is a local maximum. Now they say if f prime of x changes from negative to positive at a critical number c, then there exists a local minimum at c. And then right here we would notice here, it's just luck that it was c. Don't read too much into that. Here this was actually b, right? So that c is just kind of our normal standard way to describe a critical number, but it could be a b, a c, a d, an e, whatever you want. So it says if f prime of x changes from negative to positive, meaning that it's going with negative slopes and all of a sudden it becomes positive slopes, that means, and it was at a critical number, then that has to be a local minimum. If the sign does not change at a critical number, then there is no max or min, no local min or local max, okay, at that location. So take a minute, write all this down, okay? Pause the video if you need to so you can get caught up. Okay, so hopefully you had a chance to write all those down, but basically you could write that down and try to memorize it, but just think about it, you know, just think about if you're going up, 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 up. Sometimes I use my hands to think about I'm going up, 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 up in a positive direction. Then I'm going down, 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 down in a negative direction. Well, that has to make a little mountain. And that's where we get the idea of a local maximum. If I'm going decreasing, 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 and all of a sudden I'm going to increasing, increasing, increasing. Well, if I do that kind of like with my hands, I have to make a little valley. Okay, so if I try to think about it, you know, what it's actually doing, like trying to figure it out, it actually is creating a little valley, so a local minimum. Okay, so here's how we're going to work. We're going to use the following to help us identify intervals where f of x is increasing and where f of x is decreasing, and where the function has local maxes and local mins. Okay, so first thing we're going to do is we're always going to find the critical numbers of f of x. Okay. The second thing we're going to do is we're going to find any singularities of f of x. And in general, for us, singularities will be asymptotes or holes in the graph or something like that. Okay. Create a sign chart with the above numbers using f prime of x. So just like we did in a previous class, we're going to create a sign chart. And then recall the function is increasing when f prime of x is greater than 0 and decreasing when f prime of x is less than 0. Use your understanding of increasing and decreasing critical numbers to find local maxes and mins and intervals of increasing, decreasing. So in the previous sections, you figured out how to find critical numbers. Now we're going to use those critical numbers to find local mins and maxes, okay? And we're going to use our knowledge of how increasing and decreasing slopes affect whether it is a local min or a local max, okay? And then the most important thing, or not the most important thing, but something to just recall is that only critical numbers can be local mins or maxes, okay? Singularities cannot be local mins or maxes because local mins or maxes have to be in the domain of the original function. And likewise with critical numbers have to be in the domain of the original function, okay? So let's take a shot at an example, okay? So it says, given that f of x is equal to x squared over x minus 2 quantity squared, determine where f of x is increasing and decreasing and where f of x has any local maxes or mins. So take a minute to set that up. Okay, so hopefully you guys got all this written down by now. Hopefully you paused the video as well. Now you should be back and we can get started on this problem. So it says f of x is equal to x squared divided by x minus 2 quantity squared. So this means that I have to find my critical numbers first. In order to find critical numbers, I have to find the derivative. So the derivative is, we're going to use the quotient rule. So we take the derivative of the numerator, which is 2x, rewrite the denominator, minus, I'm going to rewrite the numerator and then take the derivative of the denominator, which would be 2 times x minus 2 times 1, right? So I just reduced the power by 1. And then I have to divide this by x minus 2 quantity squared. Okay, so let's clean this up a little bit. So this will be, let me see, they both have an x minus 2 in common. You guys see there's an x minus 2 here and an x minus 2 here. So I can factor out an x minus 2. Okay, what else can I take? They both have a 2 and an x. So let me clean this up a little bit. Let me start with the 2, x, and an x minus 2, and then let's see what's left behind. So as you can see, there's a 2x right here, and there's an x here and a 2 here. So I can take at least a 2 and an x from both of those. So, and again, factoring makes our lives quite a bit easier when it comes time to clean up. So please clean this up first. So that means that I took a 2x and an x minus 2 from this guy, and that's going to leave me behind just an x minus 2. Because it was x minus 2 squared, and I only took one of them, minus, now I took the x minus 2, I took the 2, and I took one of the x's, so there should still be one x left behind. and that's all divided by x minus 2 quantity squared. Oops, I made a mistake. Let's go back, look over here. It was already squared, and what does the quotient rule say we're supposed to do? The quotient rule says that we're supposed to square the denominator. So that means, let me go back and fix this. This should have been x minus 2 to the 4th. So let me fix this here now. Okay, so that was just a little brain typo. Okay, so now I notice that there's an x minus 2 here. I can take one of these and bring it down to a power of 3. Okay, this x and this x cancel. So then by combining like terms, so we now have 2x times a negative 2. So I actually end up with negative 4x over x minus 2 quantity cubed. Well, that's pretty nice. That I thought it was going to be way worse than that. So we actually ended up pretty good. So now what we need to do is we need to find our critical numbers. So we're going to come over here and we're going to set negative 4x equal to 0. And we're going to set x minus 2 equal to 0. I set my numerator and my denominator equal to 0. We get x equals 0 and we get x equals 2. Okay. So now we come up here. Remember, in order for these to be critical numbers, they have to be in the domain of the original function. However, 0 is, I shouldn't say however, 0 is totally fine. 0 is a critical number. Okay, because if I plug 0 into the original, right up here, if I plug 0 into here, no problems, right? I just get 0 over negative 2 squared, which would be 0 over 4, which is just 0. That's totally fine. That's in the domain. However, this guy I cannot use. He cannot be a critical number. Sorry about that. X equals 2 cannot be a critical number because if I plug it back into the original problem, I would get a domain issue, right? I would get 4 over 0, which is undefined. So it is a domain issue. So that means it cannot be a critical number. Okay, so it cannot be a critical number. However, equals 2 is a singularity, right? So we're still going to use it, but it's just not a critical number, okay? So remember, that's why you got to go back up here and kind of remember, okay, I found the critical numbers. I also need to find the singularities. Now I'm going to create a sign chart. And again, it's not about memorizing those 4 or 5 steps. It's about kind of incorporating them into like a procedure that you know how to do when somebody asks you for intervals of increasing and decreasing and local mins and maxes. So I'm going to build my little sign chart. And I'm going to use my critical number and my singularity. Okay. Some students I have seen, I don't do it this way, but some students put a little circle around that to remind them that that is not defined there. Okay. So some students do that. Okay. So then we have, sorry about that, I had to turn off my phone. Okay, so we have from 0 to 2, okay, so that means this is going to be our f prime of x. So we're doing the derivative test on f prime. Sometimes this is referred to as the first derivative test, okay? So what we're going to do now is we're going to pick values. So I'm going to do f prime, you know what, let me do this. Let me put it over here, f prime of x. I'm going to write it in red. So I'm going to do f prime of what? Well, let's do f prime of -1. Let's do f prime of 1. And let's do f prime of 3. So we're going to plug these 3 numbers in because now let's scroll up. We care about this. Right? We care about when f of x is greater, f prime of x is greater than 0, and when f prime of x is less than 0. So we're going to come back here. Okay. So when we plug -1 into our derivative, so let's go to our cleanest form of our derivative, which is right here. This is the cleanest form of our derivative. I'm going to plug a -1 into that because that's to the left of 0. And remember how intervals work. If we wrote our intervals correctly, if one of them works, they all work in that fashion. And if one of them works, or I should say, If they work in this fashion, if they all become positive, then in that interval, they're all positive. If I plug a number in and I get negative, then in that interval, they're all going to behave negatively. So any number to the left of 0 should behave like this, -1. So the top will become -4 times -1, which would be positive, and the bottom would become negative. So a positive divided by a negative is negative, so we do minus, minus, minus. Now I'm going to plug 1 in. When we plug 1 in, we get -4 times 1, which is -4, over 1 minus 2, which is -1 cubed is still going to be negative. So we end up with a negative over a negative, which is a positive. Okay, now let's plug 3 in. We get a negative over a positive. So we know that's negative. Okay. So we now have intervals of increasing. So we have our interval, you know what, I'll do it as intervals of increasing are whenever we have a positive slope. So that would be from 0 to 2. And then interval of decreasing, that would be from -infinity to 0, union 2 to infinity. Because we're looking again at this interval and this interval as having negative slopes, so those are decreasing. Now, we use this idea here. Think about this. This slope is going in this direction, this slope is going in this direction, and this slope is going in this direction, okay? Now kind of think about it. If you're going downward, 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 and you're going upward, what did we just create? Is that a maximum or a minimum? Well, that's going to be a local minimum. So right here, this is my local min, okay? Now we're going, think about this, we're going up, and then we're coming back down. So that means around here, this is going to be my local max. Okay. So we think we got everything now. So let's just go and say, well, our local min, oops, is at 0, comma what? Now let's see what happens when we plug 0 in. We would get 0 over 4, which would be 0. So it's at 0, comma 0. Sometimes your book will allow you to just say x equals 0 instead of having to find the actual point. Let me write it over here. Okay, but it is a good habit to be able to find the actual location of 0, comma 0. Now we're going to find our local max, but we got to be careful here. So when I go to plug 2 in, I notice that if I plug 2 in, I get 4 over 0, which is undefined. So that can't be a local max. And what that means is that I forgot the most important thing, or not the most important, but one of the important ideas behind this. Only critical numbers can be local mins or maxes. But remember, we discovered that x equals 2 cannot be a critical number, but it can be a singularity. So we still used it to define increasing and decreasing, but it cannot be a local max. So this is not correct, okay, even though we wanted it to be. And again, that's why I told you guys that some students I've seen in the past put a little 0, or I'm sorry, a little open circle around 2 right here on their chart, is because they want to remind themselves that it is a singularity and they can't actually touch that, okay? So this is kind of a pretty standard problem that you would see. And you should expect to see something like this on the exam and in your homework, okay? So let's move on. So we found our intervals of increasing and decreasing. We found our local min, and we discovered no local. Okay, so we figured all that out. Let's move on. Now let's try another one of these. So let me give you guys, given f of x is equal to x to the 4th minus 4x cubed, and, you know, repeat the, okay, so let's do the same thing that we did above. So pause the video, and see if you guys can answer all of the questions, the interval of increasing and decreasing, the local mins and the local maxes. Please find all of those. So pause the video and give it a shot. Okay, so hopefully you guys have done that. Let's go over it together now. So first thing we got to do is we got to find f prime. By the way, I thought that all we had to do was find the derivative and then plug, find the derivative, find our critical numbers, and then plug those into the original function. I thought that I just, in a previous video, I taught you guys that. But remember, when you were doing that, you were trying to find absolute mins and absolute maxes. So using absolute mins and absolute maxes, that is your technique. But for finding local mins and local maxes, you need to build a Sine chart. For absolute mins and absolute maxes, you do not build a Sine chart. You just plug numbers into the original function, your critical numbers and your endpoints, and whichever is bigger is your absolute max, and whichever is smaller, that's your absolute min, okay? Or whichever is the biggest and the smallest, that's your absolute max and min, respectively. So this is a slightly different style of problem. This is something where we have to use our derivative to build a Sine chart, okay? There's other ways to do it. If you were taught from another teacher in pre-calc to use a box chart, chart or whatever, that's fine too. But this is just my technique. Okay, so we take our derivative and we should get 4x cubed minus 12x squared, right? 4x cubed minus 12x squared. So now what we do with this is we set it equal to 0 and we factor out a 4 and an x squared. And that'll leave me with what? X minus 3, I believe is what you get. So that means our critical numbers are 4x squared equals 0 and x minus 3 equals 0. So x equals 3 and x equals 0. So these are my two critical numbers. And I know they're in the domain. How do I so quickly know they're in the domain? Well, it's a polynomial. And I know polynomials don't have domain issues. So both of these are going to be critical numbers. Okay, so I'm going to come over here. I'm going to draw my little Sine chart. This is my x. And I'm going to use 0 and 3. Okay. And let's see here. If I use 0 and 3, let's do let's do it in red again. I like that. F prime of -1, F prime of 1, and F prime of 4. Let's give these a shot. So when I plug -1 into the derivative, so I come over here and I'm looking at this guy right here. That's my nice clean derivative, right? When I plug -1 into there, I'm going to get a positive times a negative. So I'm going to get negative. When I put, and we know that this means decreasing, right? When I plug 1 in, I see that I get a positive times a negative, a positive 4 times a -2. So that's still negative. Still negative. And then when I plug 4 in, I see I get a positive times a positive. Okay. So we come over here and we're going to do increasing. Okay, so what's our interval of increasing? Well, it's going to be from 3 to infinity. Okay, and what's our interval of decreasing? Well, it's going to be from -infinity to 0, union 0 to infinity. Oh, I'm sorry, not infinity. That's incorrect. 0 to 3. Okay. Now, some of you might say, well, why not just do this? Why not just say then from -infinity to 3? Because this is negative and this is negative. Well, that would be marked wrong because at 0, what happens to this graph? So at 0, when you plug 0 into this derivative, you get 0, correct? That means that when you plug 0 in, you have a horizontal tangent line. Your slope is 0. So when you have a horizontal tangent, are you increasing or decreasing at that moment? You're doing neither. You have a slope of 0. So you can't actually say that the graph is increasing or decreasing at 0 itself. Around 0, you can talk about it. To the left and to the right of 0, it's decreasing. But you can't say at 0 itself, okay? And if you're wondering how you could draw that, you could do a graph like this, okay, something like that. Well, you know what, let me do it over here. You could take some graph, and I suppose you could do from this to this. So here, let me make sure this makes sense. So here, my slopes are decreasing, and here, I didn't draw it very good. So let's do, can't draw it. I can't for some reason draw it downward. I can draw it upward. Okay, so let's do this. Well, the idea is, I didn't draw it too good. Let me draw it like this. Okay, so from here, look at the slope. So here, my slopes are decreasing, they're decreasing, right, so on. And then right here is 0, but these slopes here are still negative slopes. They're still negative slopes. So this is a situation where there is, in fact, a horizontal tangent at 0. However, we did not actually get a change from decreasing to increasing or from increasing to decreasing. It just went decreasing to more decreasing, okay? Now you might notice that the concavity changed here from concave up to concave down, but that's a little bit later. Okay, we're gonna talk about that a little bit later, okay? So this is actually incorrect. You have to do from negative infinity to 0 and union 0 to 3, okay? So hopefully that makes sense to you guys. So that means then that we only have a local, remember we went at 3, we went from decreasing to increasing. So in my mind, this is what I'm doing right now. I'm going this way to this way. Well, that means I'm creating a little valley. And when I create a little valley, I'm going to create a local min. And you could say at x equals 3. But again, sometimes they will request the point. So it would be 3 comma what? We'll actually have to plug that in. So let me do 3. So that would be, let's see here, 3 to the 4th minus 4 times 3 cubed. So this would be 81 minus 81 minus, what is that, 27 times 4, 54, is that 108? So 4 times 27. So we have 81 minus 108. So we get negative 27. So we get negative 27 right here. So this would be our local min. Again, sometimes they just let you use the x value, but if they need the point, you got to go and find it by plugging it back into the original, okay? So hopefully, this is another good example using a polynomial that will allow you to find increasing and decreasing intervals, okay? There's another situation we now have to look at, a few more facts we have to come up with. So let's go here. So now we are going to deal with the second derivative test. So we can now discuss concavity. So we can say if f double prime of x is greater than 0 on a b, then f prime of x, oops, not sorry, f of x is concave up on AB. So this is now a way that we can determine concavity like I was talking about in the previous problem, okay? So F, okay, on AB, if, as you guessed, f double prime of x is less than 0 on some open interval a to b, then we know that f of x is concave down on a to b. So basically what this is saying is that if we look at the second derivative and we plug a number in and we get a positive or a negative, we can determine concavity based on the second derivative, okay? So an inflection point is where an inflection point is where a graph So when you normally are working with the second derivative, you're looking for inflection points. That will come into play more often, I believe, in Calc 3. That'll come into play quite a bit more in Calc 3. For us, we'll still use it sometimes to kind of determine shapes and pictures of graphs, but a lot of times with the graphing calculator, we can also fall back on that. So some of the stuff we're doing right now, the graphing calculator kind of defeats it a little bit. But in general, it's very important to understand what the first derivative and second derivative can tell you about a graph, because in higher levels of math, especially just for an example in Calc 2, the next math class you'll take, in Calc 2, sometimes you need to determine if a series is increasing or decreasing and on what interval. So you fall back on the first derivative test, because the first derivative will tell you when something is increasing or decreasing, and you can go to there, okay? So let me give you a little bit of a instruction. So to determine concavity, we need okay, so the first thing we would do is find where f double prime of x equals 0 or does not exist. Second thing we need to do, find any singularities. In holes in the graph / asymptotes. In the original, or in f of x. So in f of x. Okay. So not in the second derivative, but singularities are found from the original f of x, not f double prime. And then we're going to do a create a Sine chart. So we're basically going to do a test with our Sine chart and determine where f double prime or the second derivative will be positive or negative. Okay, so let's take a look at that using this process. Okay, so the problem I'd like to look at is, let's see here, let's look at this one. Over x squared is increasing, decreasing, local mins, maxes / mins. The not end. I still got one more thing to ask. Any local mins or maxes or mins, intervals of concavity, and points points of inflection. Okay. So first thing we need to do, of course, is find the derivative. So f prime of x is equal to, let's see here, we have ln of x. By the way, so this is kind of an all-encompassing problem from 4.3. You're finding intervals of increasing, decreasing, you're finding local mids and maxes, and you're also finding concavity and inflection points, intervals of concavity and inflection points, or points of inflection. So the derivative would be the quotient rule again. The derivative of ln of x would be 1 over x times x squared minus ln of x times the derivative of x squared, which is 2x, all divided by x to the fourth. Well, we see that that is actually going to be x minus 2x ln of x all over x to the fourth. So hopefully you guys can see we could factor out an x and cancel it. So this would be an x gone, this would be an x gone, so there'd be 3, that'd be a 1, that'd be a 1. So our cleanup of this would be 1 minus 2 ln of x all over x cubed. Okay, so remember, the whole point of the first derivative is what can you do with the first derivative? Okay, well, remember, you can find intervals of increasing, decreasing, and you can find concavity. I'm sorry, not concavity. You can find intervals of increasing and decreasing. You can also find local mins and maxes. So what we're going to do first is we're going to set this equal to 0. So we're going to say 1 minus 2 ln of x equals 0, and we're going to say x cubed equals 0. So we know that this means 1 equals 2 ln x, so then divide both sides by 2. So we then have 1/2 equals ln of x. So we can use the property of exponents. So we get e to the 1/2 is equal to x. So we think this is a critical number. And then this one is x equals 0, we think is a critical number. These are possible critical numbers. However, we have to go back to the original problem. ln of x over x squared. What number are we not allowed to plug into there? Think about that. We are not allowed to plug 0 in, right? For 2 reasons. Number 1, you can't have the ln of 0, and also you can't divide by 0. So this is not a critical number, not crit number, but is a singularity. Okay, so we do know that at least. Okay, now are we allowed to plug e to the 1/2 in to the original? Yeah, we can plug e to the 1/2 in. That's not going to cause any issues. It'll just be some, some ugly decimal, but it won't be a domain issue. So this is our critical number. Okay, so now what I'm going to do is I'm going to build my sign chart. And I'm going to use my e to the 1/2. Okay. Now here's the thing. Here's kind of the strange thing. Is 0 is a singularity, right? So normally I would put 0 here and I put a circle around it. But remember, there's nothing to the left of 0 because we have the ln of x. You are not allowed to use negative numbers in ln of x. So the domain of the numerator says you cannot plug any negative numbers into this problem. Okay. So this graph doesn't even actually exist to the left of 0. So this graph only exists to the right of 0. So we don't even really need to look at it as far as just make sure that when we pick our f prime value, so when we do our f prime, we do not pick anything that is, how do I say this? We don't pick anything that is below 0. So we don't pick any negative ones because it doesn't make sense to plug it into the derivative. Okay. So we're really only testing to the left and to the right of e to the 1/2. So if you take e to the 1/2 and you want to plug in some other number, let's say e to the square root of 2.7 is 1 point something, right? So I'm just going to do f prime of 1. And then over here, I'm going to do f prime of, I don't know, 4, right? Something to the right of the square root of 2.7 and some change, right? So when I plug 1 in to the derivative, which is right here, that's my derivative. So I'm plugging into there. Plugging 1 into that, the ln of 1 is 0, so this becomes 1 over 1, which means plus, 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 which means it's increasing, right? And then when we plug 4 in, we get the natural log of, you know what I could do to make it easier on myself? Instead of plugging 4, so I don't even need a calculator, I could just plug e in. Because I know that e is bigger than the square root of e, or e to the 1/2. So when I plug that into here, the ln of e is just 1, and 1 minus 2 times 1 is -1. So we're going to have a -1 over e cubed, so that's going to be minus, minus, minus. And again, you could just plug this into your calculator. I'm just doing it right now without using a calculator. So we now know that this is, oops, move the whole graph. We now know that this is decreasing. Okay, so sorry about that. So now we have, you know what, I better write it in green so we can keep track of it. So increasing, decreasing, locals. But now, since there's only one critical number, I know there can only be one local min or max. Now think about it. I'm going in this direction and coming back down. So that means I created a local max. My local max will be at, we'll say for now, x equals e to the 1/2, but if required, we could go back and find the actual value, okay? And then we know our intervals of increasing are from 0 to e to the 1/2, and we know our interval of decreasing is from e to the 1/2 to infinity, okay? So we have the answer to first part of the question. We found our increasing, decreasing intervals, and we found our local max. And again, if you need the point, you'd have to take e to the 1/2 and plug it back into here, into the original problem, okay? Right up in here, all right? So now we need something else. Now we need f double prime of x, okay? So f double prime of x, we're gonna take our derivative of 1, you know what, let me rewrite it over here so we have something. So we have f prime of x equals 1 minus log of x all over x cubed, right? So now we want to find f double prime, which is the derivative of the first derivative. So this is going to be the quotient rule once again, and this will be -2 over x, that's the derivative of the numerator, times the denominator, which is x cubed over 1, minus 1 minus 2 ln of x, times the derivative, which would be 3x squared. Okay. So let's clean this up best we can. This will be -2x squared. Oops, oops, oops. Forgetting once again to divide the whole thing by x cubed squared. So that'd be x to the 6th. Okay. So now we have f double prime of x equals -2x squared minus 3x squared plus, you know what, I want to factor this. I'm going to write this cleaner. I'm going to factor this out. This is going to be -2x squared minus 3x squared times 1 minus 2 ln of x, okay, over x to the 6th. So then I'm going to, let's see here, I'm going to factor out an x squared and cancel it. So this will become 1 and 1, and this will become 4. So what I'm left with is -2 minus 3 plus 6 ln of x all over x to the 4th. All I did was I distributed this through you guys. So that would be -3. So this becomes, let's see here, -5. You know, and I can write it a little bit nicer. 6 ln of x minus 5 all over x to the 4th. So So that is actually our second derivative. It's kind of a tough one, but in general, you guys, when you're doing quotient rules with natural logs and e to the x's and square roots and things, it's normally going to get bad. So this is our second derivative. And what are we supposed to do with our second derivative? We're supposed to find out when our second derivative would be undefined, or I'm sorry, DNE or 0. So I'm going to take 6 ln of x minus 5, and I'm going to set that equal to 0. And then I have x to the 4th, and I'm going to set that equal to 0. Well, I already kind of discovered this can't, because it's not in the domain of the original problem, we don't have to worry too much about it because the domain of this original, it has to do with a natural log. So when we come up here, once again, this domain says that x is going to be greater than 0, right? So we have x such that x is greater than 0 for this entire problem. So we really can't test to the left of 0, and we can't even use 0 in the original. So normally we would have to worry about that, but we have 6 ln of x 5 divided by 6 divided by 6. So we have the natural log of x is equal to 5/6. So just like last time, we're going to have x equals e to the 5/6. You can use the property of exponents, or you can rewrite the logarithm that says e to the 5/6 is equal to x. Remember the swirling, you can say that this is e. You can say e to the 5/6 is equal to x. So that's what I'm doing here. So we have x equals e to the 5/6. This is our critical number. It is legal. It's allowed to use. I'm sorry, not a critical number. It's from the second derivative, but it is what makes the second derivative 0. So I'm going to draw my little number line. So this is e to the 5/6. Okay, and remember, critical numbers are what make the first derivative 0 or does not exist, not the second. This is something else. So this is a number that we're going to use to test for concavity. Sometimes it will be the same number from the original first derivative, but usually it's not. So we have e to the 5/6, and we need to test, this is my f double prime of x. We need to test something to the left of e to the 5/6 and something to the right of e to the 5/6. Well, I know for sure I can do f double prime of e because e to the 5/6 is not quite e to the 1. So I know just e to the 1 is to the right of it. And I can do e to the 5/6. Let's see here. So we can do 2.7 and some changes. E to the power. I didn't bring my graphic calculator with me. So we could just do f double prime of, I don't know, 1. So when I plug 1 into there, let's see, into my second derivative, this would be 0, so I'd get negative. So if I plug 1 into here, I'll get 0 minus 5 over 1, which would be -5. So we're going to get a negative. And when I plug e into there, I get 6 minus 5, which would be 1, divided by e to the 4th, which would be a positive over a positive, which would be positive. So that means now we can say that our concave, and so by the way, I sometimes write it like this. This means concave down. This means concave up. So now we have concave, a lot of times I just abbreviate it, concave down is going to be from 0 to e to the 5/6. Concave up will be from e to the 5/6 to infinity. Okay, and remember, we started at 0 because there's nothing over here. The graph stops basically at 0, right? Because the domain of the original function is x is greater than 0. So this would be my concavity, and my point of inflection would be wherever you change concavity. So if you ever go from plus to minus or from minus to plus, you have a point of inflection as long as it's in the domain of the original function, which e to the 5/6 is. So we have a point of inflection at e to the 5/6, comma, and if you plug this in, you get this exact value. I don't want to go through and work it all out, but you get e to the 5/3. Okay. Normally for points of inflection, they want you to actually find the point, the location. Sometimes you would be allowed to just say at e to the 5, x equals e to the 5, 6, but usually, I'm just going to be honest with you, for points of inflection, they almost always want the exact location on the graph, okay? So that'll be our first video on how derivatives affect the shape of graphs. In the next video, so kind of like part 2 of this, it'll be a little bit harder and we'll go over it. But I just wanted to show you guys that particular problem, okay? All right, you guys, that's going to do it for today. Thanks for watching, and hopefully this helps you.